You don't expect corrosion like this to occur in your car nowadays.
And you don't expect rust to have weakened the structural members to anything like this extent. Severe corrosion is fortunately now only a problem with old cars.
Thanks to years of testing like that at the Rover Group Accelerated Corrosion Facility at Gaydon, near Warwick.
In 12 gruelling weeks, the object is to make Rover's new cars rust. If they can.
Stones to chip the paintwork.
Granite dust for general abrasion.
Punishing road surfaces.
Salt spray.
And a sauna in a 100% humidity chamber at 45 degrees centigrade.
It's all designed to promote an electrochemical reaction.
Just a single drop of water on a sheet of iron. At the base and in the centre, ferrous ions are being formed.
A special indicator that has been added reacts with them, giving this dark blue colour. Around the perimeter, a pink colour. The indicator has reacted with hydroxide ions.
Within this drop, an electrochemical cell has been created, but how exactly?
Well, as the iron dissolves, ferrous ions are produced.
Electrons are also produced, but these are conducted away through the metal to the edge of the drop. There, these electrons become available to react with atmospheric oxygen and water to give hydroxide ions.
Next, the iron 2+ and OH- ions diffuse away from the anodic and cathodic areas of the water drop and towards each other to the point where they react and become iron 2 hydroxide.
In a third and final stage, oxygen dissolved in the water oxidizes this to a hydrated iron 3 oxide.
Rust.
Because this rust is porous and non-adherent, it does not form a protective coating on the surface.
And it doesn't stop more iron being oxidized and more holes appearing in the metal lattice.
Rust is very permeable to both air and water, and because it's about twice the volume of the iron that it has replaced, we get a flaky deposit below which the corrosion continues unhindered.
Salt water rusts iron even faster because of its higher electrical conductivity and the fact that its small, mobile chloride ions rapidly migrate towards the anodic site where, in the presence of ferrous ions, they can produce hydrochloric acid, and that attacks iron very effectively.
So, to prevent all these reactions occurring, we must protect base steel from contact with water and oxygen and salt.
This Rover 600 is being completely broken up and examined for any evidence of corrosion that might lead to panel perforation or structural failure. It might be the fault of weakness in the design, the material used, or in the manufacturing process.
Yes, we've got a leak here. It looks as if the body white sealer bead is actually in the root of the bend all the way around the flange.
It's got to be put right, and accelerated corrosion testing is part of the process. Before the test, a panel was scratched like this.
For vehicles with Rover's 3-year cosmetic warranty after 6 weeks of testing, no more than a 2mm corrosion blister is allowed to have spread from the cross scribes.
Well, that may satisfy the warranty requirement, but did the metal have to rust at all?
Here's the prototype of a bonnet panel that has been protected with a zinc coating front and back.
Not much of a corrosion blister here.
So just how does the coating protect steel? One way to coat steel with a thin layer of zinc is to use Faraday's laws and electroplating.
And that's what this production line at British Steel's Shotton Works in North Wales does. Rolled sheet steel is cleaned by a series of processes before being introduced into a continuous run of 11 zinc plating cells containing zinc salts.
Zinc supplied as an oxide is converted into zinc sulfate in a slurry with water. This plating solution, or electrolyte, is pumped to the cells continuously.
Inside each cell, the huge lead alloy electrode is the anode, and the steel passing close to this is the cathode.
Electrolytic deposition of the zinc onto the steel, on one surface or both, gives it a coating whose thickness depends on the electric current and time.
Coating thicknesses range from 4 to 14 microns, depending on the degree of corrosion resistance required, with 7.5 microns being standard within the automotive industry.
But how does zinc prevent steel from rusting? Earlier we saw that corrosion occurred because iron in contact with oxygen and water produces a short-circuited electrochemical cell. Can we slow down the corrosion process?
The answer is yes, if we coat the steel with a sacrificial metal like zinc.
But we still get corrosion of the zinc. Let's scratch it and see what happens when we introduce water and oxygen to this system.
With two metals present, there is the opportunity for one of two anodic reactions to take place, either this one
or this one. Preferentially, the latter reaction will occur because the zinc is more electropositive than iron.
So, zinc is sacrificed in the protection of iron, and in the anodic reaction it dissolves to form the divalent zinc cation. The cathodic reaction is the same as before, but this time it occurs predominantly on the exposed steel surface.
The hydroxide ions produced combine with zinc ions to form zinc hydroxide on the zinc surface, and also to a limited extent on the exposed steel.
This is an example of galvanic corrosion.
A basic zinc carbonate is also formed by a reaction of the zinc hydroxide with carbon dioxide dissolved in the water. These corrosion products partially protect the exposed area, and the damage is partly self-healing.
But these salts only form between pH 6 and 12.5. Outside that range, the zinc is much more susceptible to corrosion.
Although it doesn't corrode anything like as fast as steel, it is attacked by acids in a crevice environment.
For instance, when two sheets are welded together. Let's explain how that can happen.
Pressing sheet steel in such a way as to eliminate the need for as many joints and spot welds as possible is obviously one way of minimizing corrosion.
It minimizes the number of crevices. But somewhere along the line there will be the need to join these panels together.
A clinch joint is made simply by bending one sheet tightly around another.
And this is a section of a clinch joint in a car door.
It should keep the water out, but we all know that door bottoms were notorious for rusting.
Why was that? Water can enter the door section through various routes, such as past the window rubbers, draining down to the bottom and getting drawn into the clinched seams,
where corrosion occurs. This is the anodic centre within the crevice.
And here is where the cathodic reactions take place, just outside the crevice.
And here is the rust between the anode and the cathode,
much accelerated by the presence of chloride ions in this confined environment, even though these concentrations may be small, as they are in rainwater, for example. This is crevice corrosion.
There are several places where corrosion of this kind occurs.
Underneath the paint film,
between spot welded joints,
and anywhere where surface coatings haven't protected the steel.
in fact, a whole battery of anti-corrosion techniques are employed to prevent corrosion.
In a clinched joint, for example, the inner panel is coated on both sides with zinc.
Whereas the outer panel will only be zinc coated on its internal surface.
The outer surface doesn't need it.
Typically, the joint is sealed with an adhesive and a sealant and should be airtight. In addition, wax is sprayed into the gap and drainage holes introduced into the inner panel to let any water out.
All this protection is needed on door bottoms to prevent them corroding. Here is a clinched joint being made on a bonnet panel.
First, the adhesive. Since 1985, when zinc-coated panels started to be introduced, the proportion of zinc-coated steel in cars has steadily increased.
Now it's between 70 and 80% on Rover cars. To clinch the outer panel over the inner one, the workpiece is put into a press.
Coating a steel sheet with zinc adds about 20% to its cost, so it is expensive and not to be used unless it's really needed.
That's why you still find uncoated mild steel in cars, in areas where paint alone is sufficient protection, such as on the roof panel, for example.
The sheet steel surface takes paint extremely well, and so on many cars, cosmetic panels like the door, bonnet and wings are electro-coated with zinc on one side only, the inner side.
In the Rover 600, about 25% of the steel used is of this type.
However, with demand for even better corrosion performance, double-sided zinc-coated steels are being used more and more.
Particularly for most structural members and the base assembly where maximum protection is needed. Double-sided zinc-coated steel is produced by a different process, and seeing how this is manufactured takes us to British Steel's Llanwern plant in South Wales.
Here, sheet steel is immersed into molten zinc at 455 to 465 degrees centigrade in a process known as hot dip galvanizing. Then, by careful heat treatment within a vertical furnace located above the zinc bath, the zinc coating is converted into a layer of iron-zinc alloy.
In the tempering process which follows, fissures develop in the surface, and these help the paint key into the coating. Also, within the alloy, a hard phase develops.
And this means that less zinc is melted out of the surface layer when it's spot welded. Molten zinc reacts with copper in the electrode, forming brass, which you can see in these spot welds quite easily.
It also affects the electrodes, which have to be redressed frequently to maintain the correct current density at the tip.
Ensuring welding efficiency has been a major achievement here on Rover's assembly line at Cowley.
But it's the cost factor that really makes the annealed hot-dip galvanised steel attractive.
Apart from uncoated steel, it is the cheapest material to use.
In the Rover 600, it has become the predominant steel type.
And there is an obvious incentive to find ways of incorporating it into the vehicle more and more, ultimately for outer surfaces too. Now for a subtle change of emphasis in anti-corrosion strategy. Can we do better than just using zinc?
Electroplating a zinc-nickel alloy provides a thinner, harder layer that's better for welding.
Increased protection against corrosion can be achieved by coating this layer.
First with a very thin deposit of chromate to help bond a lacquer onto the zinc-nickel surface.
In the oven, the lacquer is cured to give an organic polymer about 1 micron thick.
The whole sandwich of zinc-nickel alloy, chromate layer and polymer can be of the order of 5 microns thick.
Giving the same protection as the alternatives, whose coatings are a little thicker at between 6 and 8 microns.
Now this may not sound much of a difference, but the thinner the coating, the easier the material is to work with.
The main disadvantage is it's the most expensive of the coated steels.
Despite this, it is used quite extensively within the automotive industry.
So the cost equation is not always the limiting factor.
The organic polymer layer is very like a paint. So let's look at what's involved in this traditional yet ongoing method of protecting metals from attack. After 331 panels have been given 4,500 spot welds, the body in white, as the industry romantically calls its creation, is given a thorough clean, including a hot bath in an alkaline mix of complexing agents and surfactants, followed by a cold rinse before treatment with a colloidal solution of titanium phosphate.
The body in white emerges covered in minute crystals, which are going to act as nuclei for the climax of the process, full immersion in a tank containing zinc, manganese and nickel phosphate, and an oxidizing agent.
Here, the object is to coat the metal with a crystalline phosphate in a product hopefully looking like this, and in a layer up to 3.5 microns thick.
But because the material to be coated varies, it can be iron, zinc or a zinc alloy, the phosphate layer can end up having a range of composition and structure. So the chemistry of the process is carefully controlled. Its prime purpose is to promote adhesion between the metal surface and the subsequent paint layer.
Any gaps in the phosphate layer leading to the unreacted metal are dealt with by a chromate wash, which both increases the anti-corrosion performance and the adhesion of the next stage, the cathodic electrodeposition of paint.
The operator places 2 electrodes in the boot, just in case one gets snared up or falls off, to make the car a cathode.
In the tank is a monomer dispersed in an electrolyte. We'll consider it as a long-chain hydrocarbon with an amino group which becomes positively charged as it dissolves in acid. Apply the current and these cations migrate to the phosphate-coated metal.
There, the hydroxide ions produced neutralize the charge, leaving the first molecules to arrive to hydrogen bond with the phosphate. Eventually a film thickness of around 30 microns builds up, held tightly in the gaps between the crystals of the phosphate layer.
In other words, the paint is keyed onto the surface. Then the vehicle moves into an oven where some clever chemistry occurs.
First, the paint monomer flows. This will eventually give the electrocoat its smooth, even finish. Then at about 160 degrees centigrade, isocyanate groups on the hydrocarbon chain become unblocked and free to react with the hydroxyl groups.
10 to 15 minutes at 175 degrees centigrade is all that it takes to make these chemical crosslinks and form the electrocoat polymer.
The car moves on to the next anti-corrosion process. At this stage, exposed metal joints are protected with a PVC-based sealant, as is the whole of the underside of the body, to provide a tough, impact-resistant layer.
A special anti-stone chip paint is also applied to vulnerable areas such as door edges and wheel arch rims, and again cured in an oven. Next, a primer surface of paint is sprayed on to create a smooth finish. Then 2 coats of colour base coat and 2 coats of clear coat follow.
The total paint thickness, including the electrocoat, varies from 100 to 150 microns.
But we haven't finished with the corrosion protection yet.
Wax is injected into cavities which might trap water in one of the last processes before the car moves onto the line where all the components are introduced and the interior fitted out.
When the gleaming product emerges on a production line like this, it's undergone many processes to protect it from corrosion.
And some of these link right back to the time when the car was nothing more than a few lines on a computer screen. That story really starts here with Rover's engineering design group at Swindon.
Their job is to translate the stylist's design ideas into pressed steel pieces that really work when fitted together.
Put it around the rad, so that's about the limit of it. If we go any further, we'll start to reflect the door inner flange.
Can we weld it?
Can we paint it?
Can we seal it?
Are there enough drainage holes in the body?
And where are the best places to position them? As the design evolves, and there are many changes in the evolution of a new car, prototypes are tested.
At Gaydon, the accelerated corrosion tests are important, and feedback about clearances, drainage holes, and any area that might become a rust trap is presented to the design group for a rethink.
And then we duplicated the other holes, so you've got these 2 holes along the length of the door.
All right, that should be fine. All right.
Since the industry introduced warranties against corrosion, it's nice to think that they are making sure that clients will not need to worry about inherent rusting.
For the length of the warranty, at least.